Today we're going to be talking about building quadratic functions to describe situations, and this is the first part. So the first thing we're going to do is study this table and think about what you notice and what do you wonder. So looking at this table, what do you notice and what things do you wonder? So notice, just looking at this, things that we see in this. I notice that the x's go up by 1 every single time. The y's don't appear to be going up by anything in particular, just glancing at them, but they are going up. They're increasing. I notice that the y values here are all even. They're all also divisible by 4 or 8 or even 16 for that matter. All of our y's, they're all perfect squares. Perfect square meaning that you have the same number times itself to get that answer. So 0 squared, 4 squared, 8 squared, 12 squared, 16 squared, 20 squared, get you those things. And if we're looking at this, so the differences between these things, it keeps growing the further along you go. So those are some things that I notice. In terms of rendering, what the heck does this data even represent? So I have no idea what context this is, whether this is actual data or if it's just random data. We've talked a lot lately about linear functions or exponentials or quadratics, so is it one of those particularly, and how do we know? If there were another number in the table, what would it be? So these are all things that we might wonder, and of course there's other things that you might notice or wonder about this. But we're going to be seeing this data again. So here we have a rock is being dropped from the top floor of a 500-foot building. A camera captures the distance the rock traveled in feet after each second. So they're dropping it from the top of the building, so at 0 seconds it fell 0 feet. That's also very important that we're talking about how far this is falling. Okay, not the distance to the ground, but how far it's falling. After 1 second, it fell 16 feet. 2 seconds, it fell 64 feet. 3 seconds, it fell 144 feet. 4 seconds, it fell 256 feet. And 5 seconds, it fell 400 feet. So where does this data look familiar from? Aha, that table that we were just looking at. Okay, so this is representing this situation here. Alright, how far will the rock have fallen after 6 seconds? And we need to show or talk about our reasoning here. So it's important to know that this is a 500-foot tall building. Okay, so if we're looking how much it's fallen, going here from piece to piece, we've already talked about in the notice and wonder of the chart of the table that each time it's falling further from after each second. So let's look here. From 256 feet to 400 feet, it moved 144 feet, right? It fell 144 feet from that, which is more than it fell here or here or here or continuing on. So that means that here it has to fall more than 144 feet. Well, if this building is 500 foot tall and it has to move, or it's gonna fall more than 144 feet, we don't even have that much distance. So how far will the rock have fallen after 6 seconds? 500 feet. And again, our reasoning was because from 4 seconds to 5 seconds, it fell 144 feet. From 5 seconds to 6 seconds, it had to move more than that. But it had to fall more than 144 feet, but it only had 500 feet to fall. We're not going into the ground at all. Okay? Alright, so then we have Jada, and Jada noticed that the distances fallen are all multiples of 16, and that was something that we had talked about, we noticed in the chart, okay? So she wrote down each of these things and how they're broken down. Noticing that they're all multiples of 16. Then she noticed that 1, 4, 9, 16, and 25 are just 1 squared, 2 squared, 3 squared, 4 squared, and 5 squared. So she noticed that pattern. They're all multiples of 16, and they're all being multiplied by the perfect squares in order from 1 squared up to 5 squared is where we have right now. So use Jada's observations to predict the distance fallen after 7 seconds. We're going to assume that the building is tall enough that the object dropped from the top of it will continue falling for at least 7 seconds. So in that previous example, we saw that it fell, but it only had 500 feet to fall. That wasn't enough for us to get to 7 seconds. It wasn't even enough for us to get to 6 seconds. So if we're using her reasoning, okay, we would have 16 times the number of seconds squared. That means that we would have 16 times 7 squared is 49, which means we would get 784 feet. Okay? So that means that we want to now write an equation for the function with d representing the distance dropped after t seconds. So d is going to equal something. For every single one of these, this was 16 times 1 squared, 16 times 2 squared, 16 times 3 squared, 16 times 4 squared, 16 times 5 squared. That was the number of seconds squared that we had here. It even worked here, 16 times 7 squared. So here our distance is going to equal 16 times t squared, where t is standing for seconds. Okay? Now, one thing to notice from this is that quadratic functions are generally used to model movement of falling objects, and it's using this whole idea, 16t squared, in order for it to be falling. Okay? So, our next piece here, we have Galileo Galilei, an Italian scientist, and other medieval scholars studied the motion of free-falling objects. The law they discovered can be expressed by the equation d equals 16t squared, which is what we just came up with up here, which gives the distance fallen in feet d as a function of time t in seconds. So it's really important. This formula only works for feet and seconds. Okay, so if you're talking about minutes or meters or miles, if it's further out, that doesn't work here. You would have to use a conversion rate. So we have that an object is dropped from a height of 576 feet. And we want to know how far it fell in 0.5 seconds. Okay, so we want to take that 16, and our time here is 0.5, and we're going to square it because we're using that formula, distance equals 16 times t squared. Well, here, this would give us 16 times 1/4, or 25 hundredths. And when we're multiplying those two things, we would get 4. So it would fall 4 feet. Okay? In a half a second, it would fall 4 feet. All right. Moving on from there, to find out the where the object is after the first few seconds after it was dropped, Elena and Diego created different tables. So here are their tables. Okay, we have Elena's table, we have Diego's table. Okay, and our question first that we have to figure out before we're looking to fill out the tables more are, how are the two tables alike and how are they different? Okay. So, what do you notice about them? What's the same about them? Well, I notice seconds, time in seconds for both of them. That's how they're alike. Here their distance is in feet. That's alike. We have 0, 1, 2, 3, 4, and t seconds for both of them. That's another way that they're alike. And we have some sort of falling object. So those are some things of how they're alike. There could be other similarities that you see. different. How are they different? So what do you notice that's different about them? Well, one major thing is I'm looking here, Elena's numbers are going up, or so it appears, whereas Diego's numbers are going down. Why is that? Well, here, Elena is talking about the distance it's fallen. So as she drops it, or as the object is being dropped, the distance that it's falling is going up. Diego is talking about the distance from the ground. Okay, so before he drops it, if they're dropping the object from 576 feet, it's starting with that. And then it's going to fall, which means it's getting closer to the ground. And with each time, it's going to get closer and closer. It's going to have a bigger spread in between these of what's happening, a bigger interval. Okay, so that's how they're alike or how they're different. So we need to complete their tables. So we got to figure out what the heck is happening here. So Elena's talking about the distance fallen. So that means that we have 0, 16, 64. So then looking at that original chart that we had way back at the beginning of this, we've got 0, 16, 64. We're seeing those. So that means we have 144, 256. So what the heck does that mean for our equation? That means that she's just using the gravity thing here, the 16t squared. Okay? Now, Diego, when we're looking at his, here, if it's fallen for 1 second, it's fallen 16. So we would be subtracting 16. And then in the next bit here, it's fallen 48. Because if you're looking at this, from 0 to 16 is 16. From 16 to 64 is 48. From 64 to 144, it would fall another 80. So we would be at 432. From 144 to 256, we would go 112. So if we take 112 from this, we would be at 320. So how is Diego getting his information? He's starting with the 576 feet. That's the distance to the ground. And then he's subtracting the gravitational piece by we're subtracting 16 times the second squared as you go. Okay? Alright, so those are our equations, keeping in mind that we're going to be using these numbers are going to be very common of what you're seeing, and knowing that when we have an equation for the function with d representing the distance dropped after t seconds, it's going to be the distance equals 16t squared. That's it.